Let us start the day with some important definitions. Suppose we have x a p-dimensional random vector such that we have expectation of x as the mean vector mu and the covariance matrix of x to be denoted by sigma. We define the characteristic function of x is defined as phi x t to be expectation of e to the power I t prime x, where we have I to be square root of -1 and t a vector belonging to r to the power p, right. Now, this is the joint characteristic function of the components of x. So, it is the joint characteristic function for the random vector x. Now, given the information about this particular joint characteristic function of the elements of x, one can actually get to the marginal characteristic functions of the respective components that make up this particular random vector x, similar to what we had seen in the last lecture for the moment generating function. Now, this characteristic function of course completely determines a multivariate distribution, and the knowledge of this characteristic function about the multivariate random vector completely determines also the characteristic function and hence the distribution of the respective components of x. Sometimes a quantity which is used to condense the information about which is present in this covariance matrix sigma are the two following quantities. We'll just put it as definitions. So, suppose the covariance matrix of x is sigma, it is a p by p matrix. So, there are unknown elements which are present in this p by p matrix, it is a symmetric matrix. So, the total number of unknown quantities in this particular matrix is p into p plus 1 by 2. Now, in order to summarize this the information that is present in the covariance matrix, the two following quantities are defined. The first is the total variance or total variation in x. So, the total variation in x is given by trace of this sigma matrix. So, it condenses the information that we get through the covariance matrix in terms of a single quantity which is given through the trace of this particular matrix. The second quantity which is of interest is what is referred to as the generalized variance. Generalized variance of this random vector x, and that is given by determinant of sigma. So, once again it summarizes or rather condenses the information that is present in this covariance matrix sigma in terms of two single quantities, either trace of sigma or determinant of sigma. The first one is called the total variation in x. As we will see later on, that this total variation in x is a quantity of interest and which actually is looked upon as preserving type of approach when we look at principal components analysis. Now, it should be noted that the two quantities that we have defined just now, the trace of sigma, which is the total variation in x, and the generalized variance of x, are not sufficient to replace this p by p matrix sigma. So, just put it as a note that this trace of sigma and determinant of sigma can't actually replace this sigma. It is obvious actually if you look at this determinant and then the corresponding condensation in terms of trace of sigma and determinant of sigma. Say for example, if you have a sigma matrix, suppose a sigma is a 2 by 2 matrix which has elements say 2, 3 on the diagonal, 1, 1 on the off diagonal. Suppose this is the first sigma matrix, the covariance matrix. We can have another sigma matrix which is also 2 by 2 matrix which has entries as 2, 3, the same entries on the diagonal, -1 and +1 on the two off diagonals. So, these are two different covariance matrices. However, if we look at the total variation, that is, it is given through trace of sigma 1 will be equal to trace of sigma 2, and that is equal to the sum of the two diagonal elements, that is 5. We can look at the determinant of the two covariance matrices sigma 1 and sigma 2. So, these two quantities would be 2 into 3 minus 1. So, that is equal to 5 as well, right. So, the total variation that is there in this sigma 1 and sigma 2 are both equal to 5. The generalized variance of the underlying random vector x, which is given through this sigma 1 and sigma 2, both of them are also equal to 5. So, they have both of these two covariance matrices have the same measures as far as total variation and the generalized variance of the associated random vector is concerned. However, the two covariance matrices themselves are clearly different, right. So, these two quantities are not enough actually to replace the covariance matrix as such. However, the condensation that one gets is of interest at times. Now, let us move into an important concept, which is random sampling for multivariate distributions, or rather random sampling from multivariate distributions. Now, random sampling from multivariate distribution, what's basically the need of this random sampling? Suppose we have a multivariable population. Suppose we have a multivariable population with unknown mean vector as mu, which is p by 1, and unknown covariance matrix as sigma. Since for all practical purposes, when we are considering a multivariate population, these two quantities mu, the mean vector, and the covariance matrix sigma are unknown. So, the number of unknown quantities, the parameters which are actually present in that particular population are the following. So, this mean vector will lead us to p unknown quantities, because it is a p dimensional vector. So, p unknown quantities, and when we look at the sigma matrix, which is a p by p matrix, this is a symmetric matrix, it is a covariance matrix. So, hence it is a symmetric matrix, and hence the total number of unknown quantities which are present in this sigma matrix are p into p plus 1 by 2. So, the total number of unknown quantities which are present in this mu vector and the covariance matrix are p plus p into p plus 1 by 2. Right. So, in order to have inference about these unknown quantities and to have some estimators corresponding to the mean vector mu and the covariance matrix sigma, what is done is to go for random sampling from that particular population. Now, let us denote by the following quantities. Let x1 vector, x2 vector, xn vector be a random sample from the multivariate population. So, if we have that, then on the basis of this n random samples, now each of these xi's, xi vectors are p by 1, because that is basically the random sample drawn from the p variate multivariate population, and hence in order to have the inference about the mean vector mu and the covariance matrix sigma, we will be using this particular set of random sample. Now, let us denote by capital X the random sample matrix The random sample matrix, which is a p by n matrix, is basically comprising of the following vectors. So, where this x1 vector, which is the first random sample, 2 up to xn vector, which is the nth random sample. So, we have this p by n random matrix, which is actually having this entire random sample of dimension n. Now, this can alternatively be written in terms of the following. So, let us write this as y1 prime, y2 prime, and yp prime, where these quantities are having the following interpretation. So we have this xj vector is basically the jth observation vector, we have n such observations, so j equal to 1 to up to n, where this xj vector is given by the following, that this is say x1j, xpj. So each of these are p dimensional because that's the jth observation vector corresponding to this p dimensional vector, random vector. And similarly this yi vector that we had defined here, that this is y1 prime, y2 prime, yn prime, this yi prime is what is holding the observation corresponding to the ith variable. So these are basically y1 prime, so corresponding to the ith row of that matrix. So this would be xi1, xi2, xin, where this I now is from 1 to up to p. So this basically is the structure of the data matrix, where this yi prime is basically the ith row of the X matrix and xj is the jth column of the X matrix, right. Now in terms of these vectors that we have defined through the random sampling, we will introduce the two important quantities, which is the random mean vector, sample mean vector, and the sample variance covariance matrix, which would be used actually in order to have inference, or rather the inference about the unknown mean vector mu and the unknown covariance matrix, that is sigma, right. So we will have this being defined, which is the x bar matrix, x bar vector rather. This is the sample mean vector. Well, in order to have the same notation as this one, what we will denote these by capital Xi's. So let us be consistent with this definition. So you will have capital Xi's to denote the corresponding random variables, and we will use small xi's to denote the observations. So capital X bar vector is the sample mean vector, and it is given by the following. So this is a p dimensional vector which holds x1 bar, x2 bar, and the pth variables mean xp bar. So this would be given by 1 upon n, then the summation of all the observations corresponding to the first variable. So that's x1 j, say this j is equal to 1 to up to n, and the last element is 1 upon n summation j equal to 1 to n summation x p j, right. So these are the corresponding sample means of the respective variables in the X vector component. Now in terms of this observation vector, this can be written in the following way. So we can take 1 upon n outside, and then what we have here is this is basically y1 prime multiplied by I, which is of dimension n, in. So it's a column vector of dimension n with 1 as all the entries, and the last one is what is corresponding to all the variables for the pth variable, all the observations corresponding to the pth variable, where this we'll just complete this particular stuff here, so that this in terms of the random matrix what we have is 1 upon n x times in, where this in is an n by 1 column vector which has 1 as all its entries. So this x bar, which is the sample mean vector, it's a random vector once again, because it's comprising of the random variables that we have taken. So the entries of that particular x vector are given by these, which in terms of the observation vectors that we had defined earlier, the p observation vectors. So these basically are these observations vectors y I primes, and that random sample mean vector in terms of the random matrix that the data matrix that we had defined, it's 1 upon n x times I n. Now let us move on to looking at now this x bar vector, which is the sample mean vector, is what is going to be used for inference that is inference about the population mean vector, which is unknown, which is the mu quantity. Now in order to look at the other unknown quantity which is present, which is sigma, the variance covariance matrix, we introduce the sample variance covariance matrix. So the sample variance covariance matrix can have divisor either n, similar to the univariate setup, can have a divisor as n, can have a divisor n minus 1. Suppose we define that in terms of a divisor n, then this is how the sample variance covariance matrix is going to look like. So this sample variance covariance matrix, which is going to be based once again on the random samples that we have drawn, it's a p by p random matrix which has the following entries. So the 1th element of that is going to be given by this x1j minus x1 bar. Now x1 bar is what we have already defined through this random vector here, the sample mean vector. So that's what is going to be used here. Then the 1/2th element is going to be given by this x1j minus x1 bar, this into x2j minus x2 bar, and the last entry here, don't have enough space actually to write it, so this would be given by this x1j minus x1 bar, that's multiplied by x pj minus x p bar, right. So this is the matrix here. Then this is going to be a symmetric matrix, so this we only need to write the upper triangle of this particular matrix. The 2/2th element would be the one which is corresponding to the second variable. This is x2j minus x2 bar whole square. The last entry in this row would be x2j minus x2 bar, this into x pj minus x p bar, j equal to 1 to n, and the last diagonal entry, the ppth element of this matrix, would be j equal to 1 to up to n xpj minus xp bar whole square. Now if you look carefully at this sample variance covariance matrix that we have listed out here, it basically is holding, say for example this particular element, this you can associate with the variance covariance variance for the first component. So we can denote that by S11, say, then 1 upon n of this quantity is what is the sample covariance between the first and the second variable. The last entry in the first row here is the sample covariance between the first and the pth variable. So this would be S21. S21 is just this element S12 itself, because this is the variance covariance matrix. This is S22, S2p, and this would be the SPP element, where the Sij is the ijth entry of this particular sample variance covariance matrix, right. Now if we define the sample variance covariance matrix through divisor n minus 1, we will see later on that one of them would be an unbiased estimator of the population covariance matrix sigma, and the other is going to be associated with the maximum likelihood estimator when we talk about random sampling from a multivariate normal distribution. So one could have also defined this in terms of this your S n minus 1 quantity. So we can say that n times Sn would be, in such a situation, will be given by n minus 1 Sn minus 1, right, where the Sn minus 1 matrix would be this matrix what we have with a divisor here as n minus 1, right. Now let us try to write this particular sample variance covariance matrix what we have defined in terms of the data matrix X that we had introduced. So we will have this n minus 1 Sn minus 1 is equal to n times Sn. Now that, if we look at this particular matrix here, now this element here can be written in terms of summation following. I'll just write it out here, that this entry here we can write it as x1j square, this minus n times x1 bar square. So all these entries similarly can be written like this. Say for example, the 1/2th element here can be written as summation x1j x2j minus n times x1 bar into x2 bar. So keeping that in mind, we can write this particular matrix in two parts. The first part will hold the sum of squares and the cross products. So we can write that as x1j square, this j equal to 1 to n. The second entry we will just have the first quantity which I had said x1j x2j. The last entry here is summation from j equal to 1 to n x1j into xpj. This is going to be x2j square, j equal to 1 to n, and the last entry here similarly would be j equal to 1 to n x2j xpj, and the last entry pth element of this matrix is just the sum of squares corresponding to the pth component. So this is the first entry, the first block actually, and then this minus n times the sum of squares entries which we will be getting, like here n times x1 bar will come here, n times x1 bar into x2 bar will come here, and similarly the other entries will follow. So this can be written in terms of x1 bar square. The second entry will be x1 bar x2 bar. The last entry in this first row would be x1 bar xp bar x2 bar square x2 bar into xp bar, and then the last diagonal entry would be xp bar square, right. So once we have written it in this particular form, it is easy to realize that the first matrix that we have written here, in terms of the data matrix that we had introduced, that X, it is just X transpose, right. The X matrix we had defined here, which was well, we can actually, we had written this as this matrix here. Let me see, yeah, this particular matrix here, this basically is the X matrix. So if we write the corresponding entries here, x1 vector, the first component, so it will have the p components out there, then this xn will have once again the p components of that nth observation vector, and then this matrix p by p would actually lead us to the product x transpose, which would now be having the diagonal entries as the sum of squares of the respective components, and the off diagonal entries will hold the products. Now this particular matrix block here can similarly be written in terms of the x bar vector. So this is x bar vector, that multiplied by this x bar vectors transpose. What is x bar vector? X bar vector is what we have defined here as the respective x bar components for the p entries, p elements. Now we from this particular form, it is sometimes useful to reduce it to this particular form. Now this is not yet in terms of entirely the data matrix. Now as we had seen that this x bar vector can be written in terms of the data matrix as x bar vector equal to 1 upon n xin. So we can use that same thing out here. So it's 1 upon n x times in, and then the transpose of that particular vector. So this can be written as x transpose minus 1 upon n. This 1 will get cancelled out, so we'll have 1 upon n remaining, and then this is x in, then the transpose of this quantity. So what we'll be having is in prime and x prime. So we can rewrite this in a more compact form as x in minus 1 upon n in prime, this multiplied by x transpose. So this particular form what we have is what is now expressing this, the sample variance covariance matrix with either the divisor n or the divisor n minus 1 in terms of the observed data matrix. Now here in of course is an n by n identity matrix. So this is what we get. Now an alternate form of this sample variance covariance matrix is also sometimes useful. We'll just write that, say n minus 1 Sn minus 1 n times Sn, that what we have derived as x transpose into x bar transpose. So since this x vector, x matrix rather, x matrix is of this particular form, x transpose can be given by the following, that this is summation j equal to 1 to n xj transpose minus n times x bar transpose. So this can be written as following: xj minus x bar vector into xj minus x bar transpose j equal to 1 to n, right. So this form also we will today itself use this form in order to derive an unbiased estimator for the population covariance matrix, that is sigma. Now similar to the population correlation matrix, one can also define the sample correlation matrix. Say the sample correlation matrix, say denoted by R, would be say d half inverse times S, where S is either with the divisor n or n minus 1, this into d half to the power minus 1, where this D matrix is the diagonal matrix which is holding the sample variances of the respective components p in number, right. So through this diagonal matrix, if we look at pre and post multiplication using d half inverse, so what we will be getting is the sample correlation matrix, where the ijth element will actually be the sample correlation random variable for the xi and xj component of this, right. Now let us look at a bit of geometric interpretation for this random sampling. So when we talk about this geometric interpretation, we will look at two simple interpretations. Suppose we look at these as observation vectors. Let x1, x2, xn be n observation vectors. Now from these observation vectors, we had seen that one can also write this in terms of yi's. So this y1 vector, y2 vector, yp vector, these would be observations corresponding to p variables. Now if we look at the projection of any yi on 1, projection of say any yi vector on In is going to be given by yi prime 1 divided by 1 prime 1, this multiplied by this 1 vector. And what is this equal to? This is the projection, this is the projection vector, which is the projection of yi on In. So there are p such vectors, I equal to 1 to up to p, corresponding to each of these p vectors, which now are holding all the observations corresponding to these variables. So this is what is going to give us the sum of all the entries which we have corresponding to the ith variable, and 1 prime 1, this is In. I just dropped this In from all these places. So later on, actually without loss of any generality, we will just drop this particular In index. We will say that it is a vector which is holding ones, and it is of that particular dimension conforming to the other vector. So this is just the sum of all these observations, and this is going to give us n. So this is what we will be having is xi bar times In. So this basically is the vector which is of dimension n and has entries xi bar at all the places. So that's basically the projection. So this is the mean of the ith variable, and this is the n dimensional vector, and that's what has got the interpretation that it's just the projection of the yi vector, the ith vector, the vector corresponding to the ith variable or holding all the n observations on this In vector, and that's what is this. Now let us also look at the following deviation vectors. Let us denote by, say, di, the deviation vector. Now the deviation vector is the deviation which we are going to define as yi, this minus xi bar times I, right. So this is what is going to hold the following quantities, that we have xi1 minus xi bar, this is xin, the nth observation, minus xi bar. So this deviation vector is what is going to give us in each of the components the deviation of the respective observations corresponding to that ith variable. This is the first observation in the ith variable, that minus the mean corresponding to all the n observations of that ith variable. So these are this is the deviation of the first observation from its mean, from the mean corresponding to that variable, and likewise we have all these n entries like this. Now if we look at the square of the norm of this deviation vector, so if we just look at this di prime di, what is that going to give us? That's going to give us the sum of squares of these deviation quantities. So this is going to be given by xij minus xi bar square, this j equal to 1 to n. So what is this quantity? This quantity is n minus 1 times Sii. So this is actually, if we have the deviation vectors di's being denoted by this deviation, as we have discussed, that these are the deviations basically from the respective mean components, then di prime di is nothing but the sum of squares of these entries in the deviation vector, which is associated with n minus 1 times Sii, where Sii is the sample observed variance component corresponding to the ith component. So we have these deviation vectors p in numbers, and hence these also will be p in numbers. So it's basically the norm square of these deviation vectors are associated with the sample variances of the respective components with the multiplier n minus 1 as the divisor, right. Now similarly, also what we can actually see that this di prime dk, which is the dot product of the deviation for the ith variable and the dot product for the kth variable, this would be the cross product j equal to 1 to n xij minus xi bar. So, this is xij minus xi bar into xkj minus xk bar, right. And this is what? This quantity, which is the cross product between the deviation vectors for the ith variable and the kth variable. It is nothing but the covariance n minus 1 times Sik. So, where Sik is 1 upon n minus 1 of this product, which is the covariance between the ith and the kth variable. Let us also now look at the angle between these two deviation vectors. Let us denote by theta ik. Let theta ik be the angle between di, the deviation vector for the ith variable, and dk, the deviation vector corresponding to the kth variable. Then what we have is this cosine of this theta ik is going to be given by this, which is di prime dk, this divided by di prime di, this for the ith vector di, this into dk prime dk whole raised to the power half, right. So, if we have these two vectors di and dk, then the cosine of the angle between the two vectors, two deviation vectors, is given by this. And what is this equal to? As we have seen that this di prime dk is nothing but our n minus 1 times Sik, the covariance, that divided by, now this di prime di, as we had seen out here, is n minus 1 times Sii. So, this comes down to n minus 1, this as Sii. So, that is coming from this, and this dk prime dk is n minus 1 times Skk. So, this is this Skk whole raised to the power half. So, what we see is that this n minus 1 factor cancels out, and what we have as the cosine of the angle between these two deviation vectors is Sik divided by under root of Sii into Skk. That is, the cosine of this angle theta ik is Sik, that divided by Sii to Skk whole raised to the power half. And what is that equal to? That is just the correlation, the sample correlation between the ith and the kth variable. So, this gives us a nice geometric interpretation about this deviation vectors that are associated with this random sampling, that the cosine of the angle between the two is nothing but the correlation between the two random variables I and k. Now, given this particular expression here, we can say that if this theta ik, the angle between the two deviation vector is 0. So, they are basically in the same direction. So, if this theta ik, the angle between the two deviation vector is 0, then what we have, this rik is cosine of that angle 0, and hence this is equal to 1. That justifies actually our intuition that if the two deviation vectors are in the same direction, then the correlation between the two random variables would be perfect linear correlation, so that the correlation is equal to 1. Now, if on the other hand the two are orthogonal, if theta ik equal to pi by 2, so we have the two deviation vectors orthogonal to one another, then what is the value of the correlation coefficient between the two, as we would expect the two are orthogonal. So, it is moving in orthogonal directions, and hence the correlation would just be equal to 0. In the other extreme, if they move in opposite direction, not orthogonal, move perfectly in opposite direction, That is, if the angle between the two deviation vectors is pi, so the two vectors are moving in completely different but perfectly opposite direction, then what we have, this Rik is what we expect, that they are exactly in the opposite, perfect negative correlation. So this gives us a nice feeling about verifying the intuition that what happens to the deviation vectors and the angle that they are making and the corresponding values of the measure of association between the two, any two variables. So this cosine theta ik, of course, is for every pair I and k taken from the set of possible p variables. Right. Now, you remember that we had defined at the start that two quantities which are associated with the covariance matrix sigma, the total variation in x given through the trace of sigma matrix, and then the generalized variance of x given by the determinant of the sigma matrix. Similar to that, one can also define the sample quantities. So the sample quantities would be the sample total variance, one can define the sample total variation as trace of S matrix, S either with a divisor n or with a divisor n minus 1, and the sample generalized variance as the determinant of S matrix. And as we had argued that these of course gives us compression of the sample variance covariance matrix. However, these are not sufficient enough to replace S, because we can construct in a similar way to what we had seen for the sigma matrix, that it is possible to have two different sample covariance matrix giving us the same total sample variation and the sample generalized variance. Right. Now we move on to one important result regarding this estimation procedure. Now, as we had seen that we have the two following quantities, which is the x bar vector, which we are going to associate with this population mean vector, which is mu, and we have the sample variance covariance matrix, say with a divisor n minus 1. Now that's what is going to be used in order to have inference about the population variance covariance matrix, that is sigma. Now we have the following result. Let me first state the result. So let our x1, x2, xn be a random sample from a multivariate population with mean vector unknown as mu and covariance matrix as sigma. Then the two quantities that we have defined as x bar and Sn minus 1 has the following properties. Number 1, expectation of this x bar vector is going to be equal to the mean vector mu, and covariance matrix of this x bar vector is going to be sigma by n, and number 2, for the covariance matrix, sample variance covariance matrix Sn minus 1, expectation of Sn minus 1 only is equal to sigma. In other words, we are trying to say that this x bar vector, the sample mean vector, is an unbiased estimator of the population mean vector, which is mu. The sample variance covariance matrix with a divisor n minus 1 is an unbiased estimator of the population variance covariance matrix, that is sigma. Right. And the covariance matrix of this x bar vector is going to be given by sigma by n. This gives us the feeling of generalization of the univariate result what we have to the multivariate setup. We had of course similar result when we had univariate setup. Let us quickly look into the proof of this particular result. Now, in order to prove this one is quite straightforward, that expectation of this x bar is expectation of the respective components. So, it is expectation of 1 upon n x bar. Now, x bar is going to be given by this xi bar. So, it is all these observations I equal to 1 to n. Now, when we look at expectation of this, its expectation operator comes inside, and what we have is I equal to 1 to n expectation of these xi components, and expect x1, x2, xn are random sample from the same multivariate population, each having identical mean as mu, and hence expectation of each of these xi's will be equal to mu. So, what we will have this as n times mu, this divided by n, and hence that is equal to mu. So, we have this first component of this result. We can also now look at the second result, which gives us the covariance of this x bar vector, which by definition of the covariance matrix of any random vector would be given by x bar minus its expectation vector, which is mu as what we have derived, that multiplied by the transpose of that same quantity. So, what we have this is the following, that one can write this as 1 upon n summation I equal to 1 to n, then we will have this xi minus mu, and then the transpose of the same quantity, which is this I equal to 1 to n xi minus mu transpose. Now, what is this quantity equal to? This quantity would be equal to the following. Let us just split this, or rather write it term by term. So, the covariance matrix of this x bar vector is going to be given by expectation. Now, what is the first element? The first element is 1 upon n, as we had seen it is a summation of those components. So, that it will hold these quantities. So, this is x1 minus mu plus the last term is the nth random sample vector, this. Now, this multiplied by the transpose of this. Transpose of this would be given by 1 upon n, and then the transpose of the first entry, which is x1 minus mu transpose plus x n minus mu transpose, right. Now, when we look at taking expectation term by term of each of these entries with these, now if we look at expectation of this term multiplied by this term, the first term here, what we will be getting is just the covariance matrix of this x, which is sigma, apart from this multiplier. Now, when we look at the cross product, say this with the next element here, now remember that this x1 vector, x2, xn, they are random sample, and hence they are independent. So, that we will have the expectation of the cross product of this with any of these here except the first entry would be 0, because we have xi any xi being independent of xj if I is not equal to j, and hence the covariance matrix between the two would be equal to 0. So, that what we will be having is the following. After we take expectation is 1 upon n square will be there, and then we will have this when this is multiplied with each of these entries, and then expectation being taken, only the first element would give us sigma, and all the rest of the elements will be 0. When we look at the second entry here, once again the same entry here will give us the sigma matrix, and the rest of the entries will be zeros. So, we will have this n sigma components. So, these are n in numbers corresponding to these type of product, 1 being 1 with 1, 2 with 2, and n with n. All the cross product entries will be zeros because of independence of these components x1 bar, x1, x2 and xn. So, this thus gets us down to 1 upon n square n times sigma matrix, and that is nothing but this sigma by n matrix, right. So, we have proved the first part of this particular result. Let us now move on to proving the second part of the result, which establishes actually the unbiasedness element of this covariance matrix. So what we had seen, this is the second part of the result. So what we now have is this n minus 1 Sn minus 1, that is what we had seen earlier, is xj minus x bar into xj minus x bar transpose, this j equal to 1 to up to n, right. Now we had also seen that this particular term is written equivalently in the form that this is j equal to 1 to n xj prime minus n times x bar prime, right. Now we look at proving the result. So if we now look at expectation of this n minus 1 Sn minus 1, this is going to be given by expectation of this particular entire quantity. So we take expectation term by term. We will have this as expectation of xj prime, this minus n times expectation of x bar transpose. Let us give an equation number 1 to this, because we will be requiring this later on. So we need to find out those two quantities, what those two expectations are, expectation of xj prime and expectation of x bar prime. So what we realize is that this covariance matrix of xj is a random sample drawn from that multivariate population. So the covariance matrix of xj is nothing but sigma. So that is equal to expectation of this xj minus mu into xj minus mu transpose, and hence this is equal to, as we had seen in the last lecture, this is nothing but xj prime, this minus mu prime, and hence this would imply that expectation of xj prime, which is a quantity that we would be requiring in order to evaluate that expression 1, is given by this, right. Furthermore, if we recall the result that we had proved in the first part, covariance matrix of x bar is sigma by n, and that is equal to expectation of x bar minus mu, its mean, into x bar minus mu transpose, right. So by the same approach, what one can show is that this is expectation of x bar prime, this minus mu prime, right. So what we will be having is this also, that expectation of x bar prime is going to be equal to sigma by n, this minus mu prime. So this is one that we are going to use, and this is one we are going to use. So we will use this 1 and 2, or rather using 2 and 3 in 1. 1 is what? This particular expression. So what we will be having is this, that expectation of n minus 1 Sn minus 1, that is summation j equal to 1 to n, then expectation of this particular quantity. So that what we will be having here is sigma mu transpose, this minus, we have this as n times expectation of this quantity. So that is sigma, this is sigma by n, this minus mu transpose, right. So if one simplifies this, this will cancel out. So you will have 1 sigma from here, you will have n minus 1 sigma from here, and then this mu transpose term, just a minute, this is a plus sign out here, because if you take this expectation of x bar prime to this side, then you will have sigma by n plus mu prime. So this is the plus sign out here, not a minus sign. Then what we will be having here is just n minus 1 times sigma. So this would imply that expectation of Sn minus 1 is just going to be equal to sigma. So this will imply that Sn minus 1 is an unbiased estimator of the population variance covariance matrix, that is sigma. Now if on the other hand we take Sn is not going to be an unbiased estimator of sigma. Why? Simply because this n times Sn is n minus 1 times Sn minus 1, and what we have proved is that expectation of Sn minus 1 that multiplied by n minus 1, so that would also be equal to expectation of n times Sn, that is equal to sigma, and this would imply that this was actually equal to n minus 1 times this sigma. This is n minus 1 times sigma. So this would imply that expectation of Sn is going to be equal to n minus 1 by n times sigma, and which is not equal to sigma. So this proves that though Sn minus 1 with the sample variance covariance matrix with a divisor n minus 1 is an unbiased estimator of sigma, however this Sn is not an unbiased estimator of sigma. However, as n goes to infinity, this will be an unbiased estimator, and hence this Sn will be an unbiased estimator in the limit.